Now let's come to 7.2 exponential functions. So in this session we will discuss about the exponential functions and their graph. You should also pay attention to the graph. How does the graph look like? And moreover, you should be bear in mind that how can we apply this exponential function. So first of all, we would like to do some definition. So we would like to define x and y be variables such that you look at the graph, you have x-axis and y-axis. Now we define that there are two variables, and a is usually is a constant. So clearly the main rows are x and y. So a is not that important, but still we will have some subject matters, we will have some issue about a, where a should be larger than 0, so which means it should be a positive number, and a is not equals to 1. And then under this circumstance, y equal to ax is called an exponential function. So this is an exponential function with base a. First of all, you should pay attention to this. The domains. If you forget what are domains, then you should let's look at previous sessions or chapters. The domains of exponential functions are all real numbers, which we would emphasize on this because we would like to play within the real numbers system first. Next, if a is equal to 1, what will happen? Then for all values of x, y is equals to 1 to power x. So we can still have this function, but it's just a constant function. So again, it's not that interesting in our discussion. So we just put it aside first, and that's why we don't want a to be 1 first. And next, if a is negative, what will happen? Then a to power x may not be a real number. Pay attention to this one. A to power x may not be a real number. So if here I would invite you to try to think about which case that a to power x will not be a real number. Try to think about this. So you can start from a is a negative number, and then if you remember in last session, say a is -5, and x, say if x is 1/2, okay, 1/2, which is okay because we can consider x to be a rational numbers. And then what will happen to this? So this is a so a is -5 and x is 1/2, then we will have this happen, which is undefined in real number, and that's why we don't want to discuss when a is negative. So this could be happen if we consider complex numbers, but in our cases we don't want to discuss it at this moment, so just put it aside. Now these are the graph of these exponential functions, y equals to a to power x. So we have to divide them in two main parts. One is a is larger than 1. Second, a is between 0 and 1. Then we have these two different type of exponential functions graph. This one, you can see this is moving upward, and this one is moving downward. And if you remember that maybe you may heard some people say or describe some trend, say, the bacteria increase exponentially. So this is exactly the exponential way that how That's why we use exponentially to describe the phenomenon. So you can see once the function pass through 0, it will increase very quickly, very quickly. So it will look like this, increase very quickly. That's why we say exponential is quite I mean the amount to increase is quite immense, so very enormous. So these common properties, the graph both of these graph cuts y-axis as point 0, 1. So this is 0, 1. The graph the graph does not cut the x-axis. So it won't never touch x-axis. It won't never touch x-axis. So it will just lies about the x-axis. Okay, it will just lie about the x-axis. So you can imagine, no matter I give you a is 5, suppose. So no matter which index, okay, which index from -10 to +10, or from -1000 to to +1000, this number will always be greater than 0. Will always be greater than 0. Okay, so because there won't be any number that 0 to power anything will equals to 5. And even worse, if I give you 5 to any power, it won't be equals to 0. It will never turn to 0. Okay, this is very important, an idea that is very important. And this graph are image of each other when we factor in y. So this means that 1/5 x to power x and y to 5x are actually image of each other. So just look like these two, they are just image of each other. So here we did not specify a, but in imagining if a is this situation, 1/a and a are actually just the image of each other. Okay, so you can think about y is actually a mirror, so they reflect each other. So this graph, the different properties, once again on the left hand side, this graph will move upward, okay, from left to right, and when the value of x increase, the value of y increase, and so does the weight of increase of y. So here it's not only the value increase, and also the weight of increase of y will increase dramatically. So that's why it's exponentially. The weight, so the change is changing more rapidly. So the change is more rapidly. Okay. And similarly, the graph on right hand side will move down. Okay, it's the slope downward from left to right, and the value of x increase. This time, when the value of x increase, the value of y decrease, and so does the rate of decrease of y. Mean it will the change. Yeah, it is decreasing, but the change is slowing down as well. It's slowing down. So you can see that it's slowing down. It's dropped much slower. So it drops much slower. Okay, it dropped much slower. Okay, when x increase. So pay attention to these properties of exponential functions graph. Now let's try a little bit. So these figures show the graphs of exponential functions. These two, y to power y equals to a to power x and y equals to b to power x, where a and b are constants. The graph y equals to b to power x is the image of the graph of y to equals to a to power x when we factored in the right axis. Okay, so they are mirror, If the sum of A and B is greater than 5, suggest a pair of possible value for A and B. So here, if you remember what I said before, the image, so basically it just look like if B is 1 over 5, then A is 5. Okay, here you just need to suggest a pair of them, making them the sum of them are greater than 5. So let's say if I suggest A is 5, B is equal to 1 over 5, then we can obtain this mirror image, and moreover the adding of them are also greater than 5. So basically there are many answers satisfy this question. However, if you imagine it 4, then it won't be greater than 5, it will smaller than 5. But also you can it doesn't say that A and B A must be integer. So actually it's not between 5 and 4, there are still some number you can try. But anyway, there are more than one answer. You can also think about other parts of the answer. Alright, so basically the solution from the books is like this one. Okay, so the step here, this is the conclusion. Once you say that they are mirror, so you can look at here. They are mirror, you can look at here. Okay, it's symmetrical about the y-axis, so which means we have this result. Then we take this one. Actually 5 is alright, 6 is alright, and more than 1, there are many possible answers. Now let's come to the applications of exponential functions. So these exponential functions are common in real life. Many changes in quantity can be described by exponential functions, like the magnitude of earthquake or the sun intensity are actually measured in an exponential way. Let's look at some of them. So the population of a town is 37,000 in 2014. The population P of the town after T years can be represented by the following formula. So this is suggested by the question. First of all, please find the value of A. This is not difficult, saying you can suppose when T is 0, what is the population of the town? So when T is 0, which means history is 2014. It is actually 2014. Then what can you suggest? Then the population is 37,000. So you can have this one. So moreover, any number to the power 0 will become 1. So A is actually 37,000. Okay? So A is easy. Now B part. Find the population of the town in 2018. So first of all, 2018 from 2014, there is actually 4 years past. Okay, so we just say 4 is okay. So P is equals to 37,000 times 1.015 to the power of 4. Then you use your calculator and correct it to nearest 1,000. You will have 39,000. So remember to answer it in detail that the population of the town in 2000, the population, okay, let me write the answer. Population of the town in 2018 will be this one. Okay, There is no unit for population. Okay, number 9. Number 9, in a district, the number n of industrial accidents in the nth month after a stricter law is adopted can be estimated by the following formula. So K is a constant. It's known that the number of industrial accidents in the district in the third month after the stricter law is adopted is 27. So we can again find the value of K. So on the fifth month, so I suppose that this is after the stricter law. So we can formulate like this. Let me copy it again. And then n now becomes 37. And then this is the fifth month after the stricter law imposed. So we can have this. Now after using a calculator, you will get this one. And you take the cubic roots of 0.216, then you will have K equals to 0.6 actually. Now let's look at B. After the stricter law is adopted, will the number of industrial accidents in the district per month exceed 125? Now let's try it. So if this is 125, now K is 0.6 and N. So actually, you can imagine that once you learn from the exponential graph, 0.6 m, okay, it's actually dropping. Okay, let's be simple. 0.6 to the power 1 is 0.6. 0.6 to the power 2 is 0.36. 0.6 to the power 3 is 0.216. So you can see the number is they are dropping, and thus this number won't be greater than 1, and thus is actually the case won't exceed 125 anymore. So we can explain the situation like this. For M, greater than 0, so M is how many months after the law, and then this one. You should bear in mind that whenever A is smaller than 1, then whenever the index, it must be, the positive index, it must be smaller than 1, and thus 125 times is more than 125 times 1. So this N is smaller than 125, and then you answer the number of cases. Okay, the number of cases won't or will not, to be formal, will not exceed 125. Okay, will not exceed 125. So the solution basically are the same as mine. Alright, now let's look at example 10. Example 10. The mass m0 g of the radioactive element Y will reduce to mg in x days. So this is also some real life cases. In physics, it is common that we use this exponential function to help us to estimate some radioactive decay or growth. Now we have this formula. A specimen contains 100 grams of Y. Okay, so this is, what is this? this is m0. Okay, after 5 days, you say x days, so this is x. The mass of the specimen will reduce to 186.8. Find the value of A. Now you can set up the equation like this. So this is the new m equals to 100 times A is unknown, x is 5, so we have this equation, and then you will have this one, and then you use calculator. But before using the calculator, let me remind you the a to power 5, and then we would like to move the 5 to right hand side, will be like this, and then using the calculator you will have 0.972. So don't remember that this is 3 significant figures, or corrected to 3 significant figures. Okay, so this helps us to find A. Now let's look at the application. John claims that the mass of Y in the specimen will reduce by more than 25% after 10 days. Do you agree? So actually you simply put this number 10 instead of 5 into the calculation, then you will see the result. But I can remind you one thing in doing the calculation. So let me write down MMOAX. Now we want to find the new M. Then MO is 100. A here you can use 0.972, but here I would prefer, suppose I didn't use my calculator to store the numbers, the answer, then actually I can use this one. Then this will be more accurate. Or you make sure you use the make use of your calculator memory. Make use of a calculator memory also. Okay, just up to you. Here the answer will be this one. Alright, then once again I just write down, I just don't use I don't compute this number first. I just keep this number. Then I do about percentage degrees. Then I use the this number, new number minus old number over old number times 100%. It will be actually minus 24.7%. Okay, 3 significant figures. So it's basically it's dropped 24.7%. It's dropped 24, or maybe I change it to percentage change, and then I can conclude that it's decreased 24.7%. Now 24.7% is smaller than 25%. So clearly the claim, I disagree with the claim, or the claim is this, is passive void, disagreed. Alright, so that's the end of 7.2 exponential functions, the application part, and also the end of chapter 7.